Today, and we're going to talk about the melting temperature and derive the melting temperature for semi-crystalline polymer and basically creating a spherulite or a lamellar structure. So let's go back into our thermodynamics and our derivations. And again, we're going to start with basically how can we encapsulate this idea of chain folding and crystallization and our constant battle of entropy and enthalpy. And let's start with a simple case and just look at the melting of a chain folded regime. So we need to kind of define a couple of key parameters here, as we are typically want to do. So let's go ahead. Sigma is going to be the surface free energy along the growing edge of the lamella. So we're going to have to flip back and forth, unfortunately, here. So this is our sigma. So that is the growing edge. Again, the surface energy. So the surface energy, we're going to have to multiply it. Basically, oops, let me go back here. Right here. So this is our surface free energy. We're going to have to multiply that by a surface area. We also have sigma E, the surface free energy of the along the disordered folded surface lamella. So this over here, sorry, flip back and forth. So there's going to be another basically lamella right here. So these are going to be basically favorable interactions. Again, ordered. Here, there's kind of disordered mess going on here. So the lamella is going to extend here. So this is our sigma E right here. So that's the surface energy of that disordered region here. Let's go back down. X is just going to be the edge length of the lamella. L is going to be the thickness of the lamella. And Tm naught is the melting temperature of an infinitely long polymer crystal, i.e. no folds, i.e. this is going to be our 100% crystalline polymer. So how do we get this value? Well, you can run simulations and figure out the degree of crystallinity, or simulate a polymer that is basically no folds, infinitely long polymer, perfect crystal, and you could basically calculate these melting temperatures from simulation. So you have to grab that or be given those values. So to understand the free energy change for forming lamella near the melting temperature as a function of this lamella thickness, so that's what we're trying to find here. What is the Tm as a function of L? We need to keep in mind that the surface free energy, basically the total free energy change is going to consist of two key terms. So two key energy competitions. Delta Gs, which is going to be the free energy change at the surface of the crystal where the ordered region interacts with the disordered regions. So again, creating surfaces is energetically unfavorable. So that contribution should be positive. It's a penalty, because we don't want to create surfaces where ordered and disordered regions meet. It's very unfavorable for packing. We don't like to interact with each other. It's the same thing when you have like a liquid and a solid interface, these bad enthalpic interactions. Liquid, are chi of liquid and solid, or A and B, they don't want to interact. Same thing with ordered, disordered regions. So this is going to be an unfavorable. We don't want to create surfaces. But we also are going to have a favorable energy contribution, which is the change in the free energy change in the volume or bulk of the crystal. And this is going to be negative when T is less than Tm, because we want to maximize those secondary interactions. So that's kind of the idea here. So let's start and define some definitions. So the change in free energy in the volume or the bulk, basically, of our crystal, basically when we're right at the melting temperature, when T is equal to Tm naught, that change is 0. So we could rearrange this equation, and we have this expression Tm naught, so our perfect crystal melting temperature, as a function of my change in enthalpy over the change in entropy. Again, go back through your supplemental thermodynamic notes to kind of remember these expressions. So if I'm at some temperature that's like near, so close, Tm naught plus or minus, if I'm near that temperature, well, I could kind of rewrite this expression like this. So if I'm at some temperature T that's close, it could be a little bit above, a little bit below this temperature, I can now derive this expression, but I could start to plug in for some values. So you just had the expression previously that this is equal to delta H over delta S. So if we plug that in here for delta S, we rearrange this expression. So delta S is equal to delta H over Tm naught. We plug that in right here. We get this expression here, rearranging, and we get this term right here. Now, hopefully you remember what was our expression for undercoating. So delta T equals Tm minus T. So when I have high undercooling, I'm at low temperatures. What is this right here? That's just our degree of undercooling, delta T, divided by the Tm naught. So we could use and change and insert that degree of undercooling expression. And now here is our basically term for the volumetric free energy, or the free energy change in the volume or the bulk. So assuming that these are also per volume measurements. Now for the free energy, or the surface free energy, all we have two free surface energy terms. So we have surface energy, we have to go back. So we have this surface here and here. That's going to be touching the bulk, and we have this surface here and here. So all we're going to have to do is add these components. So all of those free surface energy components. So we have basically this area on the sides. Basically, I'm going to go in green. On the top and bottom, these are the surfaces that are exposed to kind of our quote-unquote our bad, our disordered regions. But all of these regions I'm going to change this to black. These regions, there's going to be lamellar extending here, here, and here, and here, and here. So these are going to be all basically favorable interactions. So when we write our expression for my delta GS, it's just going to be, so let's look at the total bad interactions first. So those are going to be positive. So I have two surfaces, my top and my bottom. So it's going to be 2 times the surface energy sigma E, and then what's the area of the surface? It's just going to be x squared plus 1, 2, 3, 4 of these x times L areas in sigma. So, but it's not going to be plus because it's going to be minus. Again, these are favorable. Actually, it will be plus because these are going to be, again, creating these surfaces is not going to be still favorable here. So we are going to get plus 4 sigma and then XL. So that's it. Because again, you're still having these, there's still going to be this surface for nucleating, even though it's going to be, even though it's going to be the one that is touching our other surface. So looking back at our definition, so this is the surface free energy along the disordered. That's going to be very unfavorable. And this is the surface free energy along the growing edge of the lamella. But again, even though it will be touching an ordered region, it is still, until we pack them against it, it's not going to be essentially in the bulk, which is this delta GV in here. Actually, where's my pen? So, oops, let me switch to my pen. Hopefully it's working. Oops, my pen is not working too well right now. Let me see if I can get it back in function. There we go. Now we're back in action. So this is going to be the total gives free energy, or the free energy for the surface area. So again, just to reiterate, here this is the surface touching the disordered regions, so it's top, bottom. Here, again, until we pack it into a next spherulite, these will be unfavorable interactions because these are exposed surfaces. So that's why it's positive here. So positive interaction because initially our little lamellar in this formalism is untouched by other lamella. So we're not in the bulk yet. So let's go back here. We can see this expression right here, just to double check. And then now the total free energy is just for the sample is just going to be, again, minus because this is favorable enthalpic interaction. So I'm multiplying by the volume here because this is, again, per volume term. We've already solved for that previously. And we're going to make one key assumption here that X is much greater than L. So this term here is going to it's the second term. So this term and this term, which has an x squared just compared to x, that is going to be much smaller. And again, we saw that x could be, very large, so on the orders of micrometers. So we're going to set that to equal to 0, and now we could solve for our problem. And we get this very kind of powerful expression right here. So let's examine this in detail. So this is saying, what happens as my L goes to infinity? Basically, as my lamella becomes really thick, basically until I extend it fully to the length of my polymer. Well, that would be like a perfect polymer, right? Or perfect crystal. Never really going to happen, but you could see as L goes to infinity, this term goes to 0, and I recover the melting temperature of my unrealistic, my simulation, my 100% crystalline polymer. But this kind of tells you, again, as L decreases, that melting temperature, again, it shrinks relative to, again, that perfect crystal. So that is kind of what we are looking at here in this expression. And we could kind of rearrange and solve L as a function of t, and Tm as well. So we'll look at that in our next expression. Actually, you can kind of do that right now. So you could rewrite this expression here, because this is just our delta T. So if we can rewrite L is equal to 2 sigma T, the x squareds cancel, divided by delta GV. And we also have this expression that we saw previously for delta GV. So we can write the length of our lamellar is 2 sigma E Tm naught, just rearranging the expression H delta T. So again, this tells us something also unique in that as my degree of undercooling, so as delta T, so this is generally always going to be positive, this is going to be positive, the surface energy is going to be a positive value. So as my amount of undercooling increases, what happens to the length of my lamella? Again, this is like the critical length to form a lamella. Basically, it's saying that as undercooling decreases, I can just form a small, like the critical lamella that needs to be formed is much, much smaller. But if I have high degree of undercooling, in order to form that lamella, I need to kind of have, again, because high degree of undercooling, there's not much, that entropic term is coming into play, so I'm going to need more of these favorable enthalpic interactions, these non-specific interactions. So we'll cover more of that in detail and a problem set coming up. But yeah, so we can kind of see and wrap this up, this discussion here. This is what we've kind of looked at previously, a little bit more in detail. And you can see that as the thickness of the lamella increases, your melting temperature hits this maximum, T naught. So again, it's in this kind of perfect, but again, as the thickness reduces, temperature necessary to melt the lamella decreases. And again, it decreases, your Tm as a function of L decreases as L basically is proportional to L, because if we have a smaller lamella as opposed to here, again, these enthalpic interactions, there's fewer of them. So you don't need a high enough melting temperature to measure them. So excellent. And you could again find that the critical lamellar thickness necessary for stable nucleation at any given temperature. So that was just our expression here. So the critical lamellar length at any given temperature or any given degree of undercooling here, we could calculate that out. Again, that's the critical amount, that is the critical thickness for stable nucleation. So again, that's the minimum that we need, once we're larger than that, we're stable. So that's kind of the expression that we have here. So we will get into more of that next time, and then also the kinetics of crystallization. So I will see you all in the next video. Thanks. Have a good one. Bye. The video is not done. Just one more note on this, because I think it's an important point to clarify. I really love this problem and this expression. And let's kind of think about this. So this, and it's going to come into more context when we look at kinetics of growth. But this is basically the critical lamella length, or the thickness, required to form a stable nuclei. So it's basically the minimum thickness required in order to nucleate lamella structure. So what this is saying is if my delta T increases, my temperature is low, we know from our Gibbs expression here, G equals H minus T delta S. If my temperature is low, this magnitude is becoming much, much, much smaller. So it's not as important. So what this is saying is that I could form a lamella, because again, this is the competition. I need these non-specific interactions between my chains in order to form a nuclei. And what this is saying is if my temperature is really, really low, my conformational entropy now term is getting smaller and smaller and smaller. I'm going to need a smaller and smaller thickness, i.e. less of these favorable enthalpic non-specific interactions like H bonds or van der Waals in order to nucleate my lamella structure. So this will become more important, or actually this will make more sense in the context of when we look at kind of kinetic considerations and this competition between nucleation and growth, and how that affects the crystallization rate as a total. So I will see you all next time. This is the end of the video, really, this time. Maybe not. Who knows? Keep watching the videos. Study well. Bye.